Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to Jure Ramadan, the last day, the fourth day of the series of Jure Ramadan webinars. Today, we'll start with an amazing lecture about waste settlement. Will be presented by Dr. Mohamed Salah. Dr. Mohamed Salah is associate professor at Ain Shams University. He got his PhD at Queen's University and did a postdoctoral fellowship at the same university. Dr. Morsi has several publications in prestige journals and international conferences in the field of geosynthetic environmental and piles and Soptic Lake. So please start.
Okay, so today we are gonna talk about waste settlement mechanisms, analysis, and design implications. So first, we are going to have like a quick idea about the landfill components, the composition of a municipal solid waste, various mechanisms of waste settlement, and factors affecting this settlement, the various models developed to simulate or represent the waste settlement, and its implications on the design of landfill liners and cover. So here, like we have a cross section for a landfill, and as we can see, we can have here like the subsoil overlain by a compacted clay liner or a geosynthetic clay liner. On the top of it, it should be an impermeable barrier, which is a geomembrane, overlain by a primary leachate collection system, and on the top, the waste. The waste composition varies from one region to another, and it depends on many factors, including mainly socioeconomic factors. These factors affect the composition of the municipal solid waste. However, it's mainly composed of organics, plastics, textiles, paper and cardboard, wood, metal, and glass. The percentage of these components differs from one region to another, as I just mentioned, due to socioeconomic factors. It's a porous, heterogeneous, and anisotropic material. So when we think about waste as a material, so it can be compared to the soil being composed of solid particles of various size, and it can be represented by a three-phase state of solids, fluid, and gas. However, it has a more complicated structure compared to soil, and this is mainly because the components of the waste undergo biochemical degradation in the presence of humidity. This results in the generation of leachate and gas, heat release, and volumetric changes. Therefore, the settlement of waste is considered a key aspect that should be taken into account during the design, construction, operation, expansion, and post-closure of a landfill. Waste settlement is time-dependent, and the final settlement value, it was found through previous studies to range between 0.25 and 0.5 times the initial landfill height. And for sure, this range varies like from the minimum value boundary to the upper boundary. It depends on the different factors that I just mentioned, the operation, the composition of the waste, and other factors. So what is the problem with the waste settlement? Why we shall study the waste settlement? So mainly, as we can see on the right, a cross section for a landfill. It's a very simple schematic, and here we can see the geomembrane base liner underlain by the compacted clay liner, and on the top of the waste there is a geomembrane cover liner. The excessive settlement of the municipal solid waste can lead to the damage of the gas and leachate collection system. It can result in the failure of the landfill cover liner, which means formation of cracks in the geomembrane cover liner or tearing of the landfill base liner. So it is necessary to predict the settlement of the municipal solid waste with the highest possible accuracy during waste disposal and post-landfill closure. Let's have a look on the different phases of municipal solid waste. And here we can just think or we can recall in our memory the consolidation of soft soil. So the first phase here, this schematic, it represents the log of the time on the horizontal axis, and on the vertical axis, the waste strain or the settlement of the waste. The first stage, just after the waste disposal and after applying a load or stress on the top of the waste, is the immediate settlement. Mainly, the stress applied on the waste may be the weight of a subsequent waste layer placed on the landfill or the daily compaction activities in the operation of a landfill. So the first stage is the immediate settlement, and it happens due to waste intermediate cover weight and or any other compaction. It ends at time called TP. Then the second stage is the primary compression of the waste. This stage involves dissipation of gases and fluids and rearrangement of waste particles. This rearrangement involves compression, sliding, and fragmentation. And here we come to the third stage, which is the secondary compression, which mainly or the main contributors to this stage is the creep and biodegradation. Creep by the effect of reorientation of waste particles and biodegradation due to the decay of organic component of the waste. Now let's see what are the different settlement mechanisms for a municipal solid waste. First is stress-dependent mechanism. Second is biodegradation of waste organic component, fluid-related mechanism, chemical reactions of inorganic waste components. Let's start by the first mechanism, which is the stress-dependent settlement mechanism. This mechanism involves the compression of waste components such as textiles, papers, cans, bottles, accompanied with release of fluids and gases. It also involves reorientation, distortion, bending, or breakage of waste particles under own weight or compaction loads. And finally, it involves also creep, that is the long-term compression of intra and inter particles pores. This involves migration of smaller particles of waste into the voids of the large particles and also the deformation and plastic deformation of the waste particles. The second settlement mechanism is the biodegradation of organic matter. The organic component of the waste biodegrades into carbon dioxide, methane, leachate, and other byproducts. The biodegradation mechanism contributes to more than 40% of the total waste settlement. And the settlement induced by biodegradation is almost equal to that induced by creep settlement. Third mechanism is fluid-related mechanism. And it's something like consolidation for municipal solid waste due to the dissipation of poor fluids leading to increase of the effective stresses in the municipal solid waste, and in subsequent additional settlements occurs. Fluid-related mechanism also involves release of intra-particle water due to external loading or biodegradation. And this ends up in reduction of particle size and skeletal compression. Finally, or the final mechanism for fluid-related mechanism is a collapse of soluble solids due to dissolution and softening of soluble solids in water. The fourth mechanism we mentioned a few minutes ago was the chemical reactions of inorganic components of the waste. The inorganic components in the waste undergo oxidation, corrosion, and combustion, and this leads to the collapse of these components, and collapse means compression and waste settlement. So let's see what are the different factors that can affect the municipal solid waste. So we just mentioned what is the composition of waste, what is the different mechanism for waste settlement. So what could be the factors that increase this settlement or results in less settlement? First factor should be the municipal solid waste composition. Second factor is the physical properties of the municipal solid waste. Third is the ambient environmental conditions. And fourth is the landfill operation approach. So how can the waste composition affect the settlement value? If the municipal solid waste has a high food content, it has a higher primary compression index, and this is similar or could be related or similar to the compression index we use in estimation of consolidation, in estimating the primary consolidation of the waste. Second factor regarding the waste composition is the particle size. If the weight of the materials or the percentage weight of materials which have a particle size greater than 20 millimeter increase, the primary compression index C sub C for the waste and the secondary compression index C sub alpha will increase. And at the end of the day, this means that a waste with higher food content, a waste with particle size ratio greater than 20 millimeter or higher ratio of particle size greater than 20 millimeter increase, the waste settlement will increase. And now let's jump to the second factor, which is the physical characteristics of municipal solid waste. First, the moisture content of the municipal solid waste. And settlement is directly proportional to the moisture content. The higher the voids ratio in the waste, the higher the settlement of the waste. And also, settlement is inverse proportional to the age of the municipal solid waste. So the older the municipal solid waste, less the settlement. And this is mostly could be attributed because already for an older waste, much of the biodegradation reactions would already occurred, so the settlement will decrease. Another factor is the ambient environmental conditions. So what could be the environmental conditions that affect the waste settlement? First, the pH value of the waste. So how could the pH value of the waste affect the settlement? And this is mainly related to the biodegradation, to the bacterial activity inside the waste. And bacterial activity at the end of the day is a chemical reaction. So a certain pH value could enhance or catalyze this reaction. So a pH of 5.6 to 8 is considered the most suitable value for the biodegradation of the municipal solid waste. And consequently, we will have a higher waste settlement. Temperature is another important factor that affects the biodegradation rate. And we can witness the highest municipal solid waste degradation at a temperature range between 34 Celsius and 45 Celsius. And within this range, as the temperature increase, the biodegradation accelerates. And in return, we will see higher gas generation and more landfill settlement. And it was found in previous studies that 42 Celsius degree is the optimum temperature for municipal solid waste degradation and gas production. We still have more factors that affect the settlement of the waste. The last set of factors that we will see now together is a landfill operation approach. And mainly three factors: the initial compaction after waste disposal, thickness of waste left, and leachate recirculation. So let's see how the initial compaction after waste disposal affect the waste settlement. The initial compaction of the waste left leads to an increase in the municipal solid waste unit weight, and as a result, the settlement of the waste will decrease, similar to the compaction of soil. The thickness of each waste lift placed inside the landfill affects the settlement also. So if the operator tends to place thicker waste lift, this will lead to higher settlement. Finally, we can get a higher rate of settlement and settlement value of if the leachate inside the landfill is recirculated. So after we saw the different factors affecting the waste settlement, let's see how can we monitor the settlement of waste. Um, uh, from research point of view, we can tell there are we can do monitoring in field or in laboratory. So in field, as we can see to the right, this was field monitoring case study reported in 2024, and we can see that field monitoring can be done by installation of certain plates, extensometer, vibrating wire piezometers, and earth pressure cell, moisture, and electrical conductivity sensors. And these are the traditional techniques. Yet, but we can have, or now there are available some more advanced techniques like the remote sensing techniques. There are two approaches, either INSAR or LiDAR. So INSAR is like a technique by using the satellite imaging. Then after getting this imaging, these images got analyzed by assuming a certain ratio between vertical movement for whatever analyzed settlement of waste or soil to a horizontal movement. Then the relative movement rate is just estimated to give an idea about if the settlement rate is increasing or in a higher rate or less rate. Another technique is LiDAR, and this can be achieved through drone surveying. So a drone will go on the top of the site, take photos for the site with accuracy that can reach 1 centimeter, and then we get this what's called orthotropic photo, which is a drone survey photo, is processed and saved as a TIF file, image file, and this ortho photo we can process it using commercially available softwares like the free version QGIS or ArcGIS. Then we adjust the coordinates of the photo and we start to draw longitudinal or horizontal sections that we can show us exactly the topography of the ground. And the advantage that from time to time you can just use this drone surveying to survey the whole area, and this is very effective if the site is not easy to access. And in the case of waste, mostly it won't be easy to access. So this could be used in research or industry, but in research, if you want to also monitor the settlement of the waste. There are two approaches. The first approach that I prefer is bioreactors. And simply the bioreactor, if we look at the photo on the left-hand side of the slide, the bioreactor is simply, it's like a tank. Inside this tank, we place at the bottom a layer of gravel overlain by soil. It could be sand. Then the waste with the composition you want to monitor. Overlain by waste. Then we can apply load on the top using a hydraulic jack. Leachate recirculation can be done using a leachate recirculation tank. And at the bottom, there should be a leachate collection for the purpose of analyzing the leachate. These bioreactors are very helpful to monitor the settlement due to primary compression, mechanical creep, and biodegradation. Because here, the waste is just placed inside the tank at whatever the ambient temperature in this region or country. So biodegradation of the waste occurs, and creep and compression also happens under the own weight of the waste in the tank, and if any load is applied using the hydraulic jack. This technique also can help us to monitor the leachate quality with time. At Inchhouse University, like we have been like monitoring the settlement of the waste in Cairo now for more over than 3 years, and actually are getting great results. So that's why I'm telling it's a good technique. The second technique is the odometer, and here it's more about only the primary compression and creep. If we are using odometers, so we are dealing with the waste exactly if it is a soil. We are here concerned only by primary compression and mechanical creep, and we did not simulate or represent the biodegradation. So someone may ask, okay, if you are gonna neglect one of the waste components, why you are using this technique? Because it's very useful to determine the value of the C sub C and C sub alpha for the waste settlement. As we will see later, a lot of the waste settlement models are just dealing with the waste as similar to soil. Third techniques, and it's not as common as the other techniques, and mainly it does not address the waste settlement. It mainly addresses the effect of waste settlement on the liner system. This techniques is a centrifuge models, and here is at the right we can see a photo for a small scale centrifuge model uh, performed by Kavazanjan in 2017. And on the top is a cross section for the centrifuge test model showing the real scale and the downscaled value. For sure, also centrifuge model does not account for biodegradation into settlement. The other thing in centrifuge models that we don't simulate or we don't use a real municipal solid waste. And here, this raises the question, why don't you use a real or actual municipal solid waste? Because simply of the scaling limitations. If I'm gonna do like a scale, for example, here, with the height of 32 meters is equivalent to 0.52 meter. So with that scale, I cannot use the waste because the particle size of the waste will be larger. That's why these kind of model are not addressing the real behavior of waste itself, but it mainly address in a approximately addresses the effect of the waste settlement on developing of tensile strains in the lining system. So biodegradation, bioreactors is considered the only one approach that accounts for mechanical compression, mechanical creep, and biodegradation. After we have seen what are the factors that affect the settlement of the waste and what are the different approaches to uh, detect or monitor or observe the waste settlement. Let's see very quickly the municipal solid waste settlement model. And the reason I'm saying quickly because there are tons of models and a lot of parameters, but mainly we need to see what are the different methods used to predict the waste settlement. Uh, Municipal solid waste there was different research done over this topic, and there was models which is called soil mechanics model, rheological models, empirical models, biodegradation models, constitutive models, and multi-phase coupling models. As an example for soil mechanics model, it's something like this, like settlement is function in the initial height of the municipal solid waste landfill, function in what's called modified primary compression index, which is similar in sense to the compression index on estimating consolidation of soil, the initial stress state, the additional stresses applied to the waste, uh, creep factor, time after the waste settlement is placed, and the only difference compared to traditional soil mechanics model for estimation of consolidation and creep is that the creep phase is just divided over different phases to differentiate between biodegradation, compression, and mechanical creep. So what is the extent of applicability of soil mechanics models? It can be used in dry landfills, and it has a great advantage that it's very easy to apply in practice because all of us as a geotechnical engineers, we are very familiar with the soil mechanics models and the different parameters. However, the disadvantage is that this model is assuming that the compressibility of solids and waste is negligible, which can be applicable in soil but cannot be applied to waste. Also, these models does not account for biodegradation of organic waste compounds. It just maybe accounts for creep at the different stages, but the absolute value of settlement due to biodegradation is not considered. The second models, which is also very simplistic models and is a rheological model. And the rheological model mainly consists of a spring and dashpot and presented by equations that describes the viscosity and deformation behavior of the waste under the influence of the applied stress. These models has an advantage that it offers good predictions for stress-related settlement, only stress-related settlement, but also does not account for settlement phases by degradation of organic matter and does not account for the variability of stresses applied to waste in a landfill. Third is the empirical models, and empirical models are mainly developed for specific landfills. If we have a certain, for example, landfills that we kept monitoring for a period of time, or if we are observing a bioreactor in the lab, we just record settlement with time and we start making or developing correlations between waste and the different factors. Uh, that's how we develop these empirical models. But the idea is that it's determined for specific landfills, for a specific waste condition and ambient temperature and uh, pH value for the waste. Yet it's very useful if we are going to depend or use these equations for a preliminary design of a landfill in similar city or with similar conditions. Its advantage that the formula are simple and easy to apply in practice, which is very important because in practice, if you get such kind of a very complicated equation, mostly it won't be easy to get all parameters and it will be inapplicable to use in practice. Disadvantage that for sure specific landfill settlement data are needed to get results. Um, Being site specific, you should be very careful on using these models. Because if the waste composition is totally different, then it will not apply to your case. If the ambient environmental condition is not the same, it will not apply to your case. And for sure, these equations might provide you with the total settlement without differentiating between the various settlement phases. The fourth type of municipal solid waste settlement models is biodegradation models. And here we have this equation is an example for biodegradation models. Like it says that the waste settlement is equals the initial waste height times the modified compression index times the log of the stress. And then the equation includes factors for the mechanical creep, rate and value, duration after stress increment, strain due to biodegradation, and constants that describes the biodegradation, and time factor for the duration of the biodegradation. Uh, the biodegradation models are very convenient for municipal solid waste with high organic content, and it could be used to predict the long-term settlement of municipal solid waste under a constant stress. And it takes into account the organic matter degradation. But let's be clear about biodegradation. The main disadvantage of biodegradation is very variable. It varies with humidity, temperature, pH of the surrounding environment. And any little or small variation in any of these factors can result in the variation of the biodegradation settlement. The fifth type of model is constitutive models, and it were developed based on soil mechanics constitutive laws, but with considering the mechanical and biodegradation properties of the municipal solid waste. Simply, these are models relating stress to strain, but considering the mechanical and biodegradation properties of the municipal solid waste. For sure, it has an advantage that it predicts various settlement mechanisms. It can predict the stress strain response of the municipal solid waste, but it's a very complicated model with so many parameters, and it's not easy to apply in practice unless it's programmed in a certain and whatever numerical modeling software. The last models for municipal solid waste model is what's called the multi-phase coupling models. And the multi-phase coupling models is kind of models just used to estimate the settlement. And each phase in the model represent a certain factor in the soil. So we will find this model includes a stiffness matrix, time factor, displacement vector, factor account for the gas pressure, and these models are suitable for estimation of municipal solid waste settlement, considering the interaction of various parameters. It gives more accurate prediction for settlement through considering the interactions between stress-related settlement, creep, fluid transport, chemical reactions, and biodegradations. But it's very complicated nonlinear differential equation, so it's not easy to apply in practice. And at this very moment, maybe we are just thinking together, okay, I just mentioned a lot of models, but we need an example to a numerical modeling that was done to represent the waste. And here, this was uh, one of the numerical models published in 2018 by you and Ro. The waste was just represented by a modified camp clay model using a finite difference numerical model. So here to the right, this is an example for a numerical modeling for the waste. The waste was defined by dry density, Poisson's ratio, frictional constant, uh, values similar to the consolidation parameters or consolidation parameters actually, time, and here also there was a factor that represents a total strain due to biodegradation. So now let's move to the last part of uh, this presentation, which is okay. So we have went through the various mechanisms that affect the waste settlement, the efforts done to simulate the waste settlement, how to monitor the waste settlement. So what is the negative implications or of waste settlement on the design? So as a geotechnical engineer, I'm going to design a landfill, for example. Why should I care about the waste settlement? First thing, let's have a look at the effect of waste settlement on liners. And here we will talk about the cover liners in the waste settlement. Cover liner is a geomembrane placed on the top of the waste and overlain mostly by a vegetation soil to cover the landfill, and then it can be transformed, like the space over the landfill can be used as a golf course, for example. Actually, the waste covers are subjected to larger differential settlement compared to the baseliners. And why the cover liners are exposed to larger differential settlement compared to the baseliner? Because simply the uneven degradation of the waste inside the landfill. And to be honest, the waste inside the landfill will not be homogeneous or isotropic. Like the waste I'm getting at this part might have not have exactly the same composition as this part. So we will have uneven degradation of the waste. And this will result in a differential settlement. So, okay, what is wrong with differential settlement of the waste and that will result differential settlement for the waste cover? The differential settlement induces tensile strains in the geomembrane line. And this tensile strains should lead to formation of holes in the geomembrane as a result of stress cracking. So here, what we see as the right is just a cross section for a geomembrane broken specimen extracted from a stress cracking test. And stress cracking and formation of holes in the geomembrane simply means leakage through the geomembrane, higher leakage through the geomembrane, and subsequent that this leakage will increase the differential settlement of the waste, and in turn it will increase the differential settlement of the cover. And a difference of settlement of 0.12 to 0.17 meter is sufficient to notably increase leakage through cover geomembrane. So this was about the adverse effect of waste settlement on tearing the covers of geomembrane. Second thing is waste settlement also has an adverse effect on the liner system of a side slope. And actually, it is something we can compare it to the down drag on piles in soft soil. So when the waste settles, the waste down drag and the differential down drag between the waste and the geomembrane on the side here, side slope of a landfill, is considered a key source for generation of tensile strains in the geomembrane. So the waste is settling, geomembrane stays in its place, so this results on down drag on the geomembrane due to the waste. As an example, based on previous research and literature, a textured geomembrane could experience a maximum tensile strain as high as 10.3% for a short-term waste settlement and about 15.5 long-term waste, long-term strain for long-term waste settlement. The strain of 10% or 15% in a geomembrane is a very high value. And if we talk about a high-density polyethylene geomembrane, a conventional acceptable value in the design of a high-density polyethylene geomembrane is 3%. So these values or strains induced in the geomembrane by the effect of waste down drag are very high and considered unacceptable. So as a designer, what can you do to reduce the geomembrane strains by the effect of the waste down drag? There are different techniques. First, you can cover the geomembrane with a high stiffness geotextile layer. Here, I'm not talking about a conventional geotextile separator layer. No, we are talking about a high stiffness geotextile. The geotextile stiffness was found that a geotextile stiffness of about 4,000 kilonewton per meter ram succeeded to decrease the strains in the geomembrane from the 10% to 2.3% in the short term and from 15.5% to 3.2% in the long term. Using geotextile stiffness that range between 4,000 to 10,000 kilonewton per meter. So this is a high stiffness geotextile. And this can be the first solution to decrease the strains in the geomembrane. Another simple solution is just change the landfill profile. So if the design includes a mild slope, this will decrease the strain in the geomembrane. And this also another thing could be achieved, could be used to decrease the strain is increasing the number of intermediate benches within the side slope. Another thing can be done is customizing the geomembrane used to the slope by adjusting the geomembrane texturings. Like you can use a textured geomembrane with a top side friction less than its bottom side. So at the bottom side, you have higher friction to increase the overall veneer stability on the side slope, and on the top, less friction, so to decrease the friction between the settling waste and the geomembrane, and in turn decreasing the strain in the geomembrane. So at this point, let's summarize this lecture. So what are the key points or the take-home message we can get out from these lectures? First thing is that the waste settlements is equal to about 25% to 50% of the waste height. Estimation of waste settlement is crucial to optimize the landfill airspace and design of liners. The magnitude of waste settlement is affected by various factors. First is the waste composition, temperature, waste height, compaction effort, and waste age. The total settlement of waste is summation of immediate settlement, long-term settlement due to mechanical creep, biodegradation of organic content, and flow of liquid and gases. Also, we found that settlement models were developed to estimate settlement. Modern models accounted for hydro, chemobiochemical settlement, but such complicated modern model is not easy to apply in practice. The waste settlement and differential settlement shall be considered on design of liners in waste cover systems. Excessive differential settlement induces tensile strain in the geomembrane cover that could lead to an increase in leakage through the holes formed. Finally, waste down drag induces tensile strains in geomembrane-based liner that could exceed the allowable 3%. This tensile strain could be reduced by covering the geomembrane by a high stiffness geotextile flattening the landfill side slope and using a geomembrane with a top side friction angle less than its bottom side. So here we have reached the end of this presentation, and many thanks for listening to the presentation.
Thank you very much.
You are
A
welcome.
lot of
Thank you.
work. Yeah, like it's a great work. You covered like most parts related with landfills.
Thank you.
So, any question to Dr. Muhammad? Yes, Anas, go ahead.
Yeah, thank you for your presentation. I had